Hi, this is Michal Koutsky, and I would like to tell you something about our recent work with Mike Sachs from Rutgers University about sketching at a distance. So let me first start with what do we mean by at a distance. So at a distance is a measure of string similarity, where we measure for two strings x and y, how many operations do we have to make to x to get y. And what kind of operations we are thinking of? Well, we are thinking of deletion, so I can delete a symbol from X. I can insert new symbols, J, for example, into X. And I can actually substitute some existing symbol W for some other symbol G. So the minimum number of operations which takes me from X to Y, that's the edit distance. It's a symmetric measure, and it has many applications, like in bioinformatics for comparing proteins or genomes, to text processing for processing text. So people actually looked at this measure for quite some time, and there are known many algorithms for it since already basically like 70s. So we know quadratic algorithms and slightly faster algorithms, and this is known to be essentially optimal under the strong exponential time hypothesis. And but there are some slightly better algorithms if you actually parameterize the running time by the actual edit distance of the two strings. So if k is my edit distance, then you can actually get algorithm k times n, which runs in times k times n. That was by Yukonin. Or you can get algorithm which runs in times n plus k squared. That was done by Mears and Landau-Wishkin. So what we actually will be focused in this talk on is exactly this parameterized setting where we have some parameter k, and we are looking for what I would call threshold k edit distance, where if the edit distance between x and y is below k, I want to know exactly the edit distance, and if it's above k, then I just want to know it's above k, so it's large. So I distinguish between large case and the small case, and in the small case, I want to know exact answer. And these kn and n plus k square algorithms can be made into these parameterized algorithms. So if you give me the parameter k, I have an algorithm which runs in times, say, n plus k squared, and it tells me if the string is above the threshold or below, and if it's below, it gives me the answer. So that's a computing at a distance. But over here, we are actually interested in sketching. So in sketching, you give me a single string x, and I want to compute some sketch of x. So the sketch of x should be some kind of condensed or compressed version of x, but maybe x is uncompressible, or rather think of it as some extracted feature of x. And so if I take sketch of x and I take a sketch of some other string y, and these sketches are computed when I'm computing the sketch for x, I don't know y, and vice versa. So they are kind of like independent of the other strings. But from the sketches, I should be able to compute the edit distance of x and y. And in this setup, I actually don't want like arbitrary edit distance, but it will be this case of threshold k edit distance. So if it's below the threshold, I want to actually exact edit distance between the two strings. And if it's above the threshold, then I just want to know that it's large. What's the measure of success in this case? Basically, you want to minimize the sketch size. So the sketch size should be as small as possible. And when you are computing the sketch, you actually know the parameter k. So your sketch might actually depend on the parameter k, and it may not actually work for other thresholds k. So what is our result? So our result is a sketch which is of size linear in k times some small factors which depend on it. So in particular, our sketch size is of size k times 2 to the square of log n times log n, which is over here. Now we should think of this term which has this 2 to the square of log n as relatively small. So it actually grows slower than any polynomial factor. So if you think of like n to the epsilon, this function actually grows slower. So if k would be something like n to the half or n to the 1/4, then actually this is a negligible. The best you can hope for information theoretically is that actually you will have a sketch of size order k. So that would be, or roughly k. So this is close to optimal in terms of dependence on k. course, we would like to improve this other term, but at this point, we don't know how. So what was known before? So we are not the first sketch, actually. We are like a sketch in a line of work. And the first sketch, actually, which appeared about like 8 years ago, had actually size k to the 8. And that was quite surprising result because even non-uniformly, we don't know whether such sketches exist. And this was actually the first sketch which achieved anything non-trivial. So then there was a line of improvements. There was k cubed and k squared. And now actually we are improving these results even further to this almost linear dependence. And this is kind of nice or surprising because for many of these, as you have seen for the algorithms, there is this bottleneck k squared under the strong exponential time hypothesis. And it wasn't clear actually in this context whether over here this k squared is also a necessity or not. So we do get actually below this k threshold, k squared threshold. So let me tell you now a little bit about our technique and our tools. So our work actually starts from the work of Bhattacharya and myself last year, where we get this k squared sketch. And it was based on a string decomposition, which was introduced in that paper. So let me tell you a little bit about that, because that's also a starting point for our improved sketch. So in the string decomposition, you have a string X, and you want to divide it, partition it into blocks, and each block actually should be small. How small? Well, we actually measure the size of that block in terms of its description. So it should have small, efficient description in terms of grammar. And by grammar, I just mean the usual CFL context-free grammar. And so each block has a grammar, and this grammar should be of size roughly order k. So this string decomposition gets a parameter k, and it chops the string into blocks of size so that each block has a size order k. But that's not all. There are more properties of this string decomposition which are actually important for the sketching application. And that's when you actually take two different strings. So when you get a pair of strings x and y, and you run this string decomposition on each of them independently, with high probability, what happens is that you end up with basically decomposition which is compatible with the edit operations. So what I mean by that is that the decomposition is going to have the same number of grammars, G1 up to GS, and moreover, all the edit operations will be always contained in some between some pair of blocks, and the number of blocks which actually contain these edit operations is at most k. And in particular, if you want to compute the distance of x and y, you can just actually look on the pairs of the grammars which differ from each other, look on their block, compute their edit distance, and sum it up, and that's going to give you the edit distance of x and y. So in that sense, this decomposition is actually compatible with the edit operations between x and y. All this is under the assumption that the distance between x and y, the edit distance between them, is at most k. Then this happens with good probability that the decomposition is compatible. Now, once you have this, it's actually very easy to create a sketch which will have size roughly k squared, and that's exactly what the previous sketch was. So what you do basically, well, this string decomposition basically makes the question from edit distance, it transforms it into a question about Hamming distance. Why is that? Well, because if you just look on the grammars from left to right, they are nicely aligned except for these k grammars, k pairs of grammars which may differ. So in particular, now if you encode each grammar by some fixed size block of size roughly k, then the grammars in x and in y, if you just like concatenate them as a string, they will actually differ in at most k of these pairs, and each of the grammar actually has description of size roughly k. So in altogether there is exactly like about like k-square places you need to recover and find out what is the distance between x and y. So if you can actually recover these grammars, then from those grammars you can recover the blocks, you can calculate their eddy distance, and you can actually compute the eddy distances of x and y. So for this, what you need a sketch for Hamming distance, which will be able to handle about like k-square errors, k-square differences in the strings. So that's my capital K. And the sketch will have to be able to actually output the content of the different positions. So not only that you want to calculate how many different positions are there might be up to k-squared different positions, but for each different position, you actually want to know what was in X and what was in Y. And there are sketches like this. And for example, there is one recent one which was done by Clifford, Kotsumaka, and Porat in 2019, which can actually recover these positions and their content. And it has some additional nice properties, which I'm not going to discuss here because they are not actually necessary for our results. But you could do basically with anything, any other, you could get a sketch. So the only thing you need is to be able to recover the different places, different positions, and that's it. You can make sure that if the two grammars differ, of course, if they are encoded in binary, sometimes just the places may look the same, but you can make it so that if the grammars actually differ, you can make sure that they look different, because you can use different symbols depending on some, say, checksum or hash value of the grammar itself. So there is an easy trick which can guarantee you that if the two grammars differ in somewhere in one bit, then they actually you will be able to recover the whole grammars. So I'm assuming that's actually what we have at our disposal. So this is what was done before, and why is this sketch actually not sufficient, or where the sketch is losing? Well, the reason why the sketch is losing is because you have to recover k pairs of grammars, and each grammar has size k. But there are kind of like two extremal cases. In one extremal case, all the edit operations are actually contained only in like single block of X and single block of Y. So there is actually just one pair of grammars which differ. And then you will need to recover like k bits, because there might be k bits of information there. And on the other hand, maybe there is actually the edit operations are spread among these grammars, or maybe you might have actually k pairs of grammars which differ, but each grammar, basically, if you expand the blocks, it's going to differ only in single bit. So the sketch basically have to be handled both these cases, and this k-squared is the trivial upper bound. So what you could do better? Well, in the case where the errors are spread, it's kind of inefficient to use k bits to encode each grammar. So a natural idea is to try to actually decompose the strings further, and that's actually what our approach is. So we actually are going to apply this decomposition procedure recursively. So first we start and we split X into blocks. Each block has grammar of size roughly k. Then we take each block which we got and we subdivide it into further grammars, but grammars of size k half. And then we iterate this further recursively. So after roughly log n rounds, you will end up at blocks which have descriptions which are of size roughly constant. Now, what do you want to recover in this case? Well, in this case, it's natural to actually shoot for to recover actually the kind of like the appropriate grammar. So what would be the appropriate grammar? Well, it would be the grammar which is of size which is comparable to the number of edit operations which is among the particular blocks. So, for example, over here, G12, that would be a block in which there is roughly k half edit operations. Then there is this other block, which is children of GT minus 2, and there is going to be K4 edit operations over there hidden. And there is another grammar which has even like fewer operations, and so it's going to be like really tiny, and we recover it as a tiny grammar. So that's kind of what we would like to do. So we want to actually, each grammar should basically be responsible for the number of edit operations, which are roughly its size. So that's kind of what the optimal would be. And then we are hoping that the sum of these calls to recover these grammars will sum up to linear, and which would be the case. So how are we going to recover them? Well, there is a easy kind of like a obvious solution. So we are going to sketch each level of this grammar tree independently by Hamming distance sketch as before. So over here, each slice, basically we slice the tree and we sketch it using a Hamming distance sketch as before. And now what we want actually, we want to basically from each slice, we want to recover the grammars which are the right grammars, so they have the right number of errors actually behind. So this is kind of like our goal. So what are kind of the difficulties which you are going to encounter? So one difficulty is that, of course, over here, this GT minus 22 actually already contains some, it's actually, the grammar in X and Y actually differ because the blocks actually are not different. They are different because there is some grammar which actually eventually we want to recover. So already these grammars differ. So we don't actually want to recover the whole grammar. Actually, we don't want to recover this grammar at all. We ideally would not like to recover anything about it. But luckily, we can actually choose an encoding where the difference, encoding which actually has the property that if the blocks, the actual blocks have L edit operations between them, then the grammars differ at most in L positions. So somehow this grammar G2 T minus 2, which we don't want to recover, is actually just going to contribute by at most L Hamming differences to this whole level. So in total, the grammars which we don't want to recover contribute by at most K Hamming distances. And then there are these grammars which we want to recover, and they in total also contribute to at most K differences in a Hamming distance. So if we just sketch the whole level, then and our sketch will be able to recover order K Hamming differences, then we will be doing fine actually. So that's actually the good news. So that's our plan. So now you can think, okay, so are we done? Well, the issue is not quite. So what is the problem? Well, the problem is that this grammar, so we want to recover it over here because G12 actually already contains enough edit operations. But since it contains enough edit operations, actually, when you subdivide further and you look on its children actually are going to contribute to the next level Hamming difference. And the problem is that we actually lose control over these children. Once the number of edit operations in the block is actually more than the grammar size into which we are subdividing, there might be actually misalignment between the grammars. So the grammars may actually get shifted because maybe in one string we get two grammars and the other one we just get one, and the whole following grammars may actually be shifted. So that's an issue, and we have to actually deal with it, and we are dealing with it using a tool which we called Hamming hierarchical mismatch recovery scheme. So let me tell you about that. So this is exactly the solution to our problem. Which so maybe let me just go back and let's just see what the problem is. So the problem is that this part, these blue grammars actually may generate a lot of Hamming differences, which are for us completely irrelevant, but they are going to basically flood this level by Hamming mismatches, and we won't actually see this orange part, which is what we are after. So the problem is that there might be some parts which produce so many errors that we won't see actually the relevant. So we want to actually suppress the blue part and recover only the yellow, the orange part. How do we recover it? Using this hierarchical mismatch recovery, which actually has exactly the goal to suppress this blue parts. So how do we do it? So what's the definition? So in the hierarchical mismatch recovery scheme, we have two strings, X and Y. Think of it, that's the encoding of the grammars. And the strings are divided into blocks. So over here, we have blocks over here. And we look on how many differences are there between each pair of blocks. So that's L00. So we call that load of that node. So in this case, that's a load of a leaf. So the load of the leaf is just the number of differences in Hamming distance between the two blocks. So, and now we are going to actually calculate what's the load of the parent. So we build a tree above these blocks, and the tree basically kind of matches the grammar tree. And over here, we are going to compute the load of the upper nodes. What is the load of the upper node or any inner node? So the load of inner node is actually summation of the loads of its children. So the number of differences below here. But if you would just let it propagate like this, then again, like it would be like overwhelmed by errors from parts which just generate like too many errors. So we are going to cap it at some threshold. So each level is going to be associated with some threshold, which we call capacity, and we are going to basically bound this load at a given node by the threshold for that level. So over here, we basically sum the differences below the tree, and we take a minimum with the capacity. And the load of this node is this minimum. So it's never more than the capacity. And if it's actually below capacity, then it's the true load. So what is capping actually, what it has effect? So if there are too many errors actually below that node, then they are actually capped at the capacity. But if it's below capacity, then they are actually propagated above. So now in this tree, we can actually identify nodes which somehow pass through nodes which don't contain too many errors. So we say a node is overloaded if its load is actually substantial fraction of its capacity. So K over D in particular. So if its load is more than kappa over D, where kappa is its capacity, then we say the node is overloaded. What we want to recover in our case, in our application, we want to recover basically differences from blocks, which on the way to the root pass only over through the nodes, which have capacity always bigger than the actual node. So it is by factor D, actually the capacity is always bigger than the node, where D is actually the depth of the tree. So this gadget actually allows you to basically focus in the previous application where we are sketching grammars. It actually allows you to suppress this blue information, which we don't want to recover, and it is going to actually recover the yellow parts. Maybe it will also recover some part of the blue stuff, but that's fine. The important part is that it's going to recover the orange stuff, which is relevant for us. You can build these hierarchical mismatch recovery schemes, basically using standard technique for building Hamming distance sketches. So that's actually very nice, and we think that this might actually be useful in other applications as well. So that's roughly how our sketch actually proceeds. So we take the hierarchical mismatch recovery. We set the capacities roughly to proportional to the grammar size which we have, and each level is actually sketched by such a mismatch as a hierarchical mismatch recovery scheme. So what we get eventually is a threshold at a distance sketch. Which is this size which I promised. So it has k times 2 to the square of log n size. And not only that, it actually recovers the edit distance, but it also actually recovers the optimal number of sequence. So this is a bit a byproduct of our algorithm because we have to run this algorithm many times. And for various species of those two strings X and Y, we are actually getting various candidates for the edit operations, and we have to run it multiple times, and we basically are taking kind of like the majority output. So that's why it is actually important for our algorithm to recover the edit operations, not only not only the size. So this is basically for our results. So what is basically left, or what's interesting? So of course it will be very nice to get rid of this 2 to the square of log n times log n. So that actually comes from a black box usage of embedding of edit distance into L1, which actually helps in approximating edit distance. So we use results of Ostrovsky-Rabani, which has this kind of distortion factor. So that's basically like their approximation factor is 2 to the square of log n times log n. So if you can actually improve their distortion, then you can immediately improve our sketch size, because we actually rely on it in black box manner. So that's one obvious question. But much more interesting question, which I find much more kind of like fundamental, is can we actually get interesting, so sublinear size sketches for approximating edit distance with a constant factor? So that's I think is the major open problem. Thank you.